In part 1 of lecture 6, we will answer the question, what is bottom-up parsing? Top-down parsers start at the root of the parse tree, and from there, build the tree. What we are doing, whether we realize it or not, is building the parse tree as we traverse it pre-order. Bottom-up parsing is the exact opposite. As we collect tokens on a stack, we will build tree fragments from these tokens and from simpler tree fragments until we have put together the entire tree. Bottom-up parsing is emulating the Pushdown automaton, the theoretical machine that processes context-free grammars. The machine consists of a set of states and a stack. The states allow you to keep track of where you are as you process the grammar and the program that you are looking to translate. The stack keeps track of the portion of the program that you have already read. Bottom-up parsing is easier to automate because you are emulating the push-down automaton. Also, unlike the top-down parser, bottom-up parsers can parse any kind of context-free grammar. Bottom-up parsers are called shift-reduce parsers because these two operations make up almost all of the actions that will be taken. Shifting involves moving the current token onto the stack and getting the next token from input. Also, the machine will shift to another state based on the state in which it is currently in and the token that it just has used. Reducing is more complicated. It involves popping all the variables on the stack that make up the right-hand side of the production and replacing them with the non-terminal on the production's left-hand side. While it is tempting to think of shifting and reducing as simply being pushing and popping, that is not the case. Shifting involves moving to another state and fetching the next token. Reducing also involves pushing the appropriate non-terminal on the stack. Most bottom-up parsers are table-driven. The table has encoded in it all of the information that you need about the grammar. This means that you can use the same driver each and every time, with the only changes being stored in the table. That action will depend on the current state and on the current input token. As a result, the machine's current state reflects both what the machine has already parsed and what it expects to see. There are several parser generators that can be used to create a bottom-up parser for the compiler writer. The best known is YAC, which stands for Yet Another Compiler, which came as part of Unix, along with its lookalike, Bison, which is actually part of the GNU project. Bottom-up grammars are referred to as LRK grammars. The L stands for left-to-right scanning, from beginning to the end. The R means that the parse tree is right-derived, in other words, bottom-up. The K indicates the number of look-ahead characters. There never should be a need for more than one look-ahead, so we will refer to these as LR1 grammars. This example is an expression grammar that is a little different from what we saw in the previous lecture. There are a few reasons for it, but essentially, it's a simpler grammar. Again, we have expression derives expression plus sign term, or simply a term. But the next production is different. Term derives plus sign and factor, or minus and factor, or simply factor. All of our terms will have only one factor. Also, factor derives identifier or constant. There are no expressions in parentheses in this grammar. We are going to expand our grammar a bit, breaking the productions with alternative right sentential forms into separate productions. But we will add a new special start symbol, which we will call S. which will derive our regular start symbol, followed by the end of file marker. Other than that, the grammar is essentially what we saw before, separation of alternative right-sentential forms. This is what an LR0 parse table looks like. We will discuss how to create it later. You will see along the left side the states that comprise our state machine, numbered 0 through 12. The column after the state is for the actions. In all but state 12, the action is either shift or reduce by a specific production. Keep in mind that reducing by 2 productions are 2 distinct and different actions. In the case of shift, you will see a variety of different states to which we will go, depending on what the look-ahead is. So for example, if the look-ahead is identifier and we are in state 0, the state to which we will go is state 6.